Well, hello everybody. Thanks a lot for joining. We're going to go ahead and get started. What I wanted to do is talk to you a little bit about, I'm not sure I'm pronouncing this right, but VitOS or VITOS. It's a Thunder data project. It also has the name Silent Angel associated with it. I don't know a ton about the history of this product, but I did discover it in the Roon community, and I was a little skeptical at first, but I thought I would give it a try. As many of you know, I've been a big fan of using Diet Pi as a Roon endpoint for a long time, as an endpoint solution for the Raspberry Pi. The reason I like Diet Pi, if you think about the name, it's because it's a very lightweight, very thin, very kind of quiet. It's a very small, compact installation. What we want for an audio endpoint is for it to be as low noise, the lowest possible CPU utilization. We want it to be very, very quiet. So we tend to use these underpowered or very low power CPUs, and then we run an operating system on them that's really not doing much of anything. All we want that endpoint device to do is read some audio data from the network and copy it out to an attached USB DAC. So we want that device to be very, very quiet and really not doing much of anything. And Diet Pi struck me as a pretty good solution for that, because a default installation doesn't really have much of anything running. There's only about, when I look at kind of the list of tasks that are running with HTOP, I'll typically see something on the order of 11 or 12 threads, maybe up to 16 or 17 if I'm logged in and poking around. But the number of background tasks is very, very low. The CPU is almost entirely idle all the time, even on like a Raspberry Pi 3A or other low-powered device. So it helps us to have the quietest possible kind of connection, network connection for our DAC in the Roon ecosystem. So again, I'm speaking primarily within the context of Roon. I know that you can use these endpoints for Spotify Connect. You can use them for DLNA and other things. But that's mostly outside of the context of what I'm talking about today. So I'm talking about using a Raspberry Pi as a Roon endpoint device to connect your USB DAC. Again, Diet Pi has been a long-time favorite, but I read some stuff about VitOS and thought that maybe I should just give it a try. And I was pretty impressed by what I heard. I wasn't really expecting much of any difference at all, but it did seem to make an audible difference. I found that when I was listening with VitOS, the sound was just a little bit more relaxed. I don't know that I could describe it in a ton of detail. What I tend to do when I'm evaluating really small changes like this, and don't expect like a large night and day change, but I'll tend to just put that change in the system and just listen to it as I normally would do for a week or so, and then take a look back either at my notes or my best recollection of my behavior and see if it changed at all. So did I tend to have longer listening sessions? Did I listen to albums from start to finish, or did I skip around a lot? And I found that with VitOS, it did improve that listening behavior. And so it seemed like kind of a worthwhile upgrade, and it's surprisingly simple to set up. So before I go into kind of a walkthrough of how that whole setup and installation process works, it's pretty well documented, but I will kind of unbox all this stuff and show you what that looks like. Before I do all of that, I wanted to set up some kind of rational explanation for maybe why it does what it does. So the theory that the VitOS guys have, the folks at Silent Angel, the theory that they have is that if we decrease network latency, then there's a correlation between low network latency and network performance and the sound quality that we get out of these endpoint devices. Now, I have no idea if that's true or not, or how to really kind of verify. Sound quality is kind of a subjective thing. I don't know or have the instrumentation necessary to objectively measure the analog output of the DAC, for example, while feeding it from, ROPI versus Diet Pi versus VitOS versus other solutions and other configurations, and try to figure out how that's impacting the sound that's coming out of the analog outputs. The only thing that I know is just my subjective experience when I'm listening to these things. And it's not like a double blind thing, but I don't think in an A/B test you're going to be able to hear a difference between these things anyway. It's a very subtle difference. Anybody who says that like veils were lifted and they're mind blown at how different ROPI sounds to Diet Pi or VitOS are just kind of, I think they're, the power of suggestion has taken over a little bit. The differences are pretty small, but you know, it's all these things are basically free or donationware, or they're very low cost, and it only takes a little while to set them up. So I think it's fun as a hobby, and that's what this is. It's fun to experiment with them and try them out and see. But I wanted to see if I could measure something objectively. I didn't have a way to measure objectively the sound that's coming out of the analog outputs, but I could measure network latency. So I took a look at in my network. I've got a managed switch that allows me to mirror traffic from that's going on one port to another port, so that I can set up Wireshark and observe that traffic. I'll just show kind of really quickly what that looks like. Let me switch to here. Let me hide this so this doesn't get too confusing. So, all right. So, in my network, I have a switch, and I can, if I want to, I can go to one of these switch ports, and this is the one that I've got my Mac connected to, and I can optionally, I'm not going to do it now because it'll take me off of the stream, but I can switch this to mirroring. That enables me to watch traffic that's happening on another port, on the port that I'm interested in analyzing. So what this allows me to do is have my laptop passively listen to a conversation between my Roon core, my Roon server, and the endpoint device, and then I can observe the traffic and latency that's happening on that port. And the reason I want to do this in kind of a passive way, if I were to run a packet capture on the little Raspberry Pi device, we end up with this sort of observability problem that running that packet capture might generate load on that device and cause it to behave differently. So I want my device that I'm using for observing the traffic to be separate from core and separate from the Raspberry Pi. And so having a managed switch with this mirroring feature enables us to do that. So it's a little bit of a geeky type of thing, but hopefully that makes some kind of sense to some of you. And if it doesn't make any sense, you'll just have to trust me that it worked okay. You can ask me questions later on. Anyway, so this is the VitOS for Raspberry Pi website, thunderdata.com/VitOS for RPI. So you'll want to bookmark that page and come back to it later on. I usually just Google for VitOS space Raspberry Pi, and this is one of the things that comes up right away. They do have a number of other products that you could explore as well, but again, for the sake of this discussion, we're going to be talking about the Raspberry Pi 4. Now, a couple of constraints for VitOS relative to other solutions you might have used. One of them, this does require a wired connection. So if you're using endpoints over a Wi-Fi connection, VitOS is not going to be an option for you to explore. Unfortunately, it does require a wired connection. Again, their theory is that reducing latency to the absolute lowest possible is what can improve sound quality. And if you're using a Wi-Fi connection, latency is going to be like an order of magnitude or two higher than what you're going to be getting over a gigabit network connection. So Wi-Fi is kind of off of the table for VitOS, unfortunately. Also, as you can see in the product description name, it's explicitly for Raspberry Pi 4. So if you have a Raspberry Pi 3 or compute module like in a Allo US bridge, this is not going to work. You might be able to get it to install, but the processor is just not powerful enough to run a real-time kernel and be able to keep up with audio, was what I've heard people reporting. So going to need to have a Raspberry Pi 4, going to need to have a gigabit or a wired Ethernet connection here. So those are kind of the requirements. He goes into some explanation of kind of what the features and capabilities are, and how they've made some changes to the kernel and USB I/O and the task manager to try to make this operating system perform better as a streaming solution. So I wanted to verify some of the network performance. If we go down to the bottom of this page, we can see that he's done some testing. He's played this song, I Love You, from, or the song Mr. Blues from the album I Love You. I haven't looked at that particular album, but I played Blue and Green from Kind of Blue. It's a the audio file that I tested was 24 bits, 192 kilohertz, so similar in format. And I wanted to see if I could duplicate some of these results. But you can see here in his test setup, he has average latency, max latency, and standard deviation. different values that he's calculated for these things. So I wanted to try to reproduce those results. So I went over to, I installed Wireshark, like I said, and set up my laptop so that it could monitor the traffic going between the endpoint device and core, so I could kind of see what was going on. And I created some PCAP files, and I'll just open some of these so we can take a look and see what we look at. So let's take a look at the VitOS one first. So this is the packet capture of all the communications going between the endpoint and my Roon core machine. I'm going to do some filtering here so that we can get just the packets that we're interested in. And then I will take a look at some latency statistics. So I'm going to go here to round trip time. And I know this is very nerdy, but stay with me. I know we've gotten some questions from folks that are like, you know, why should I consider using VitOS versus something else? And I want to make sure that you understand that the theory is that lowering latency, round trip time, is going to have a positive effect on audio quality. So we want to make sure that VitOS actually does what it claims it does. So they claim that they've worked on something in some kind of way with a real-time kernel and a different scheduler and some different optimizations at the OS level to achieve better network latency. So if we can't verify that claim, that's objective, right? Then everything else kind of goes out the window is kind of my thinking on this whole thing. So let's take a look at the round trip time latency between endpoint and core. I'm going to try to zoom in at a consistent level here. Just give me a second to zoom in a little bit more. All right, cool. I want to have kind of a consistent range here. So we'll look at the first kind of couple of milliseconds and zoom in so that we can see this is our performance for round trip performance with VitOS. Now let's open up another packet trace. Let's look at Ropey. And I know this is very nerdy, just bear with me. We're going to go to statistics, and let's look at round trip time again. You'll see me cycling through to identify the right stream. I want the stream that has most of the data. So you can see over here, this stream has 387 megabytes of data. That's about how big that track is. I think with Ropey it's stream number 4, but let me see if I remember right. I haven't rehearsed this at all. I just came up with this crazy idea yesterday. All right, so already we can see, if we take a look at the y-axis here, that we've got this spike that's above 60 milliseconds. We're trying to have a y-axis, a round trip time that tops out at 2 milliseconds. So I'm going to have to zoom in quite a bit in order to get these graphs to look similar. And it means that we're not going to be observing all the data. Let me just do this real quick first. So we can see we've got some points up here that are at 8 milliseconds. Let's zoom in one more time so that I can try to get these to look more or less similar. I think right about there ought to get it for us. All right. So this is ignoring some of these lines, these latency lines that go really, really high. They're like, much, much higher. All of the round trip time for VitOS stayed, below this 1.5 millisecond type of range, it looks like. And if we look at Ropey does something kind of weird. I don't really understand why, but I was able to reproduce this. I ran a couple of different tests with Ropey, and for like the first half of the song or so, there was this kind of pattern of latency, and then for the rest, we had a different pattern of latency. And then we can see that there's a little bit more of a more consistent pattern. So just visually, we can see that there's something different going on between these two, but we need to do a little bit more analysis. So let's see. I've written a little Python script that takes a look at these round trip time values. And essentially, in Wireshark, you can go to export packet dissections and export this whole thing as a CSV file. So I did that, and I created CSV files. Let me just show you. Let's take a look at this file. It's a comma separated file, and then the last field in this file is this packet round trip time. So I've got these values for the entire trace, and I can run a little Python script that will allow me to kind of average all those values, determine what the maximum one is, and work out the standard deviation. I'm not sure. I might have missed the maximum one. This maximum is showing the maximum latency from the Diet Pi perspective, or the endpoint perspective, not from the server perspective. So we don't see those really large values here, but we can see what the average latency is and what the maximum and the standard deviation. We want kind of all of those values to be as small as possible. If we take a look at VitOS, we get these values. So we can see that the average latency is, I don't know, maybe it's like about 50% lower. The maximum is lower. Oh, I'm looking at Diet Pi, good grief. Let me look at, I'll say, wow, the ROPI values look really good. This is what happens when you don't rehearse this thing. Okay, here we go. So the ROPI values, the average latency was, 0.183 milliseconds. Maximum is 8 milliseconds, and the standard deviation is, 0.175 milliseconds. And for VitOS, we can see that the numbers across the board are lower than that. Diet Pi, I didn't show you a plot for Diet Pi, but I can open that up and see. Diet Pi is kind of somewhere between those. Diet Pi, in many respects, is pretty close to VitOS, but VitOS is clearly better. And then both of those are quite a bit better than what I got with ROPI. And then I did a similar thing with ROPI XL. And we can see that the average latency for ROPI XL is even bigger still. In this particular case, the maximum kind of varies a fair bit, but the standard deviation and the average tell, I think, a pretty good story that there was a lot more variation with ROPI XL than there was with ROPI, and that was greater than Diet Pi, and that was greater than VitOS. And we could open up, let me just, since some people, I talked about Diet Pi and I used Diet Pi quite a bit. Let me open the dietpi.pcap file just so we can take a look at its plot. And then as you might guess, ROPI XL is going to be sort of worse than all of them. Go to statistics, round trip time. Oh, there's my mom chiming in here. I should have sent her an invitation, actually. I usually do. All right, here we go. Here's the Diet Pi one. Let me zoom out a little bit so I can get our scope set to a consistent level here. All right, cool. So where'd the other guy go? My windows are not very much to scale, but we can see Diet Pi versus ROPI. Diet Pi is quite a bit better behaved. If you look at the graphs, I mean, there's not a ton of difference visually between Diet Pi and VitOS. In fact, VitOS has a couple little samples that are a little bit higher even. But what you'll notice if you kind of squint your eyes is that the density of points at this sort of 3/4 of a millisecond level is higher with Diet Pi than it is with VitOS, and that's what drives these values for VitOS, particularly the average, down lower than what it is for Diet Pi. So at least we have some kind of objective measure that VitOS is doing something different. We want to just understand why you should even bother with it at all. At least it seems like it's doing what it claims to do regarding reducing network latency, and that's verifiable. I encourage you, if you've got the interest to do the same kind of thing, you can ping me later on, and I'm happy to give you some advice on how to set up Wireshark and do this kind of analysis if that would be helpful for you to understand why this thing works the way that it does. But that is the theory. Again, there's a bit of a leap between, yes, we can verify objectively that VitOS reduces network latency. There's a bit of a leap from that to, because network latency is reduced, that it sounds better. I don't really understand why there would be a correlation. There are probably a lot of other things you could measure around the Raspberry Pi performance. For example, you could measure the temperature of the CPU, and maybe whichever endpoint software has the lowest CPU temperature is the one that sounds the best. We want to try to correlate some kind of objective measure with the subjective experience of enjoying music on these things, and it's not really kind of that easy to do. CPU temperature is tricky because monitoring CPU temperature causes CPU temperature to go up, and the ambient temperature in the room and airflow conditions can make a big difference on temperature, or at least at the level of granularity that we're dealing with here. So I didn't bother trying to do that kind of analysis. There's other things that you could look at too, but right now the VitOS guys, the Silent Angel Thunder Data folks, have given us a pretty interesting objective way to take a look at endpoint performance, and then it's up to us to try to draw any kind of conclusion around sound quality for that. So all right, cool. I will now, now that we've kind of covered what this thing is doing, if you go to this website, the instructions are pretty simple. Step number one, and I mean the documentation is really nice for this as well. I like the way this is laid out. But you can click on this download link to go over and download this from SourceForge. I'm not going to do this because it's going to steal bandwidth from my stream, so I'll kick out of here. But basically, you download the image. If you've got Etcher, Etcher is a pretty popular solution for Linux, Mac OS, and Windows for flashing that image to a micro SD card. You can't just copy the image to the micro SD card. You have to actually flash it as a binary file. And I walked through in my video how I do that. I had already an existing VitOS Raspberry Pi set up, and so I just used that to flash the micro SD card for a second Raspberry Pi, and I'll be showing that here in just a bit. Then you shove the micro SD card into the Raspberry Pi, connect power and Ethernet, and then with Ropi, as you know, there's a web interface that you use for configuring things like which DAC it's going to use or what your time zone is and all these other settings. VitOS doesn't really have settings, and so they don't really have a web server set up to manage these things. But there is a little server running on it somehow, because you're able to connect to it using a mobile app. It's a little bit of a different approach, and a lot of people are like, oh, I don't want to install another app on my phone, but it's a pretty lightweight app. It seems to behave itself well, passed all of my phone's security checks and everything, so I'm not too worried about it. And the reason that this app exists at all is to provide you with a way to, in an authorized way, install Roon Bridge. So Roon Labs consider their software their proprietary IP, and they own the copyright. They don't want other people, other manufacturers, or other individuals including that software in their software, the Roon software that they wrote in any kind of third-party product. So if you buy an off-the-shelf product, it should come without Roon Bridge or Roon's server or any of Roon software installed, and then it should provide a mechanism by which you can, click or initiate the installation yourself as the end user. And so that's what these guys have done. And they've chosen to do this using a mobile app rather than a web interface. And really, that's kind of the only thing. So you use this mobile app to connect, to discover your VitOS device on your network, and then manage it. And by manage it just means it connects to it and allows you to install Roon Bridge. And it's just a kind of single tap install. The other thing that's nice about the app, though, is, for example, you might have a DAC that acts a little bit wonky with Roon Bridge. So if you disconnect or power off the DAC and power it back on, Roon might have trouble kind of finding that DAC again. There's a button on the app that you can use to restart Roon Bridge on the VitOS device, and that'll usually cause it to kind of pick up any changes to DACs that you had, that if maybe a DAC has gone asleep or gone offline. And so I've occasionally used it for that. And then you just enable the output in Roon and enjoy. And then again, there's more information on here, like just what we went through about the network performance improvements. So with all of that, I think what I'll do is bring up myself doing a demonstration of the assembly process. Don't pay too much attention to that window, but I need to get where am I? I need to get us to the assembly side of things. All right, so I made this. I pre-recorded this part because you don't want to see me dropping screws on the floor and yelling at the cat and all the other things that I tend to do when I'm having trouble with manual dexterity things. But these are the little parts that you need. I bought a power supply. I had this Kodi case. It's a flirt case that's Kodi branded. It costs the same as a normal flirt case, but if you buy the Kodi branded one, then the Kodi folks get a little bit of a donation. So since it's $15.95 either way, I usually buy the Kodi branded ones when I need one. I like the flirt case because it's a passively cooled solution. So you'll see in a moment once I get it open, there's a kind of a heat pipe inside of it that wicks away or takes the heat off of the CPU. See this little post? That's going to kind of come down in contact with the CPU on the Raspberry Pi itself. There's some heat conducting tape, whatever you call that we'll put on the processor of the Raspberry Pi to make a thermal connection between the CPU and GPU on the Raspberry Pi and that little post. And once this thing's put together and it's been running for a little while, if you put your hands on the side of the case, which is all aluminum, you can feel that it really is kind of warm, and it does a good job of keeping the Raspberry Pi cool. When I tried putting the Raspberry Pi in a standard official Raspberry Pi case, even with some heat sinks on it, the typical temperature for the Raspberry Pi, just doing nothing, just running Diet Pi with no music playing and nothing happening, was around 65 degrees Celsius. And it starts thermally limiting the CPU as you start getting closer to 80 degrees, I think. Definitely by 80 degrees, the CPU performance is going to be compromised. But with this flirt case, even if the Raspberry Pi is pretty busy, it tends to stay below 50 degrees. And when it's just idle, it's closer to 40. So I'm just kind of demonstrating where you want to put this. You want to put that thermal tape on the actual CPU itself. It's a double-sided, so you kind of peel off the one side and then press it down on the CPU and then peel off the little plastic on the other. Very important to get that plastic stuff off of both sides before you put this together. It'd been a little while since the last time I put one of these things together, and so I was thinking you put the Raspberry Pi on that bottom piece and then shove the top of the case on top of it. Unfortunately, that did not work. You have to put the Raspberry Pi into the metal case and then place the bottom of the case on top to get it all to fit together. Otherwise, you just can't get the little input ports to line up, and you can see me struggling here. I left this in the video though because it's a common mistake that other people might make. So when you do yours, if you decide to build this with a flirt case, do what I'm doing now. I'm holding it a little bit out of the camera, but put the tape on the Raspberry Pi and then press the Raspberry Pi into the flirt case. Make sure that all the ports line up properly on all sides, and once you've got all that good, then you can set the back of the case down and put the screws in. It'll work out way better for you if you do that. So learn from my mistakes. That's kind of the point of doing these things in the first place. So yeah, you'll watch me kind of fumbling with the screwdriver here. But I usually recommend putting them, because we're still kind of wanting to make sure that we get that CPU seated as well as we can onto that post. So I recommend going kind of a diagonal pattern when you put the screws in, so that we don't have that plate in kind of a cockeyed fashion. If you just put two screws in on one side, the other side might be popped up a little bit. So if we do them in a diagonal way, crisscross, I find usually that helps to make sure that the pressure is as even as possible. I don't think it matters tremendously, but since we're engineers and we're being nerdy, we might as well complete the picture here. So yeah, so that's, as you can see, the assembly of this thing is pretty straightforward. You've probably done Raspberry Pi cases before, but I like this solution, especially for an endpoint where I know that I'm not going to use a hat. There's no way to use a DAC hat with the flirt case. It doesn't expose the GPIO pins, and there's no space at all inside to put anything. But if I know that I'm going to be connecting whatever peripherals I have via USB, I think these little flirt cases are a nice way to go. So next step is to get that micro SD card ready. As is typically the case when I try to peel these things open, this is a SanDisk one. I think I peel the corner off and it just breaks, but I just use my screwdriver to kind of scratch a hole around it and get the little card out. In this case, rather than using Etcher, I'm going to use my existing VitOS machine to flash this card. So I'm just kind of showing you where it goes. But I'll get my card reader. This is attached. The other end of this is attached to another little Raspberry Pi that's running VitOS already. So I'll bring up a terminal window and walk you through how I flash from Linux. So sometimes, if you don't want to deal with firing up Etcher and flashing it that way, you've got a Raspberry Pi that's already running someplace. You just download the images, you can get them loaded. You can see here that I'm looking through my shell history, so I don't have to remember what command I used, but and then the command that I found was for ropey instead. So I need to specify the image file for VitOS, and you can see that I'm setting the block size of 4 megabytes, and I'm doing this fsync thing that I found on the Raspberry Pi webpage. So we wait a little while. I cut out the flashing time because it takes a minute or so. We can see that it wrote things out properly. Those are the images that I have downloaded because I wanted to do tests of the performance, network performance of all of those. And I used the same Raspberry Pi to flash all the other ones. LSBLK just shows that we've got we've got SB1 and 2. Those are the partitions that are flashed. I like to run that just so that I can convince myself that the things were written out to the card right, that the partition table that VitOS needs exists properly. So once that's all done, we can take that card and transfer it to our new Raspberry Pi. In this case, it fit a little bit snug, and I wanted to make sure that sometimes it's possible to get it in between the card, in between the slot and the case. So I wanted to make sure that it was going in properly. So just pay attention, look closely. If it looks like it's putting up a fight, then probably the card's not going in right. And that's kind of our device. The next step is to use the Raspberry Pi power supply. Some people will try using a linear power supply, and there's a bunch of other solutions that are pretty good. For these Raspberry Pi 4s, I tend to favor just using the official Raspberry Pi power supply. It seems to work pretty well, and it's reliable. I've got some iFi, iPower X 5-volt power supplies that work pretty well with these as well. So, but this $8 power supply from the Raspberry Pi Foundation works and sounds about as good as anything else that I've tried. So I think you can definitely do worse. I've got power networking connected. I'm just leaving right now to plug the other end of that power cord into the wall so we can get this thing energized and get it booting. It doesn't take very long for it to boot. I think I waited longer in this video than I really needed to. But we'll wait just a second for me to come back. The next step after this, once we can take a look at the kind of the lights on the network card. It was tough for me to get this lined up with the camera properly, but we can take a look at the lights and see that there's some network activity. At least we know that things come on properly. The next step is to go to our smartphone and find that VitOS Manager app and see if we can connect to this thing. We need to connect with the VitOS Manager app so that we can tell VitOS to go out and download Roon Bridge from Roon Labs, get it installed, and start it up. That's kind of the next step. So you can see I already have it installed, but I'm just going to go to the Google Play Store and show you where to find it. I'm not very good at typing on these things, especially when a cable's connected to my phone, so forgive me for futzing around a little bit here, but we'll bring up VitOS Manager. That's what the icon looks like, orange with this sort of logo. And it's looking for my other VitOS device, so I told it I want to manage a new device. You're probably not going to have that issue. You'll just connect to the VitOS image that you have running on your network. If you have more than one, though, you can switch among them using this thing. And next, we'll just click on Install Roon Bridge. There's some information about Roon Bridge, including a Learn More link that we can open that'll take us to Roon Labs. And we'll just go ahead and get this thing downloaded and installed. And now we can go to Roon. Now, I was about to go into Roon and try to configure this endpoint when I realized that at this moment, I didn't have a USB DAC connected to this thing. So if you don't have a DAC connected to an endpoint that's designed to be used with a USB DAC, Roon won't be able to find it. Roon Bridge will it'll come up and it'll say the RAT protocol will look for available DAC drivers, and if there's no USB DAC connected, it's not going to find any, and so Roon won't be able to find the device. So this is me scurrying around trying to find a DAC. I had this VitOS tone board that I put together before, and so it's a quick and easy DAC to just plug into this thing and give us a DAC that we can use so that we can get this endpoint set up. So plug this guy in. I typically recommend powering a DAC separate, not using the Raspberry Pi to power the DAC, but in this case for this test it's fine. It certainly works okay. All right, now we can go try to find it in the audio settings. There it is there. And I'm going to just put in a name for this. You can see the default name for the VitOS device is Raspberry Pi 4 or something or other. It's too small for me to read right now, but that's what you'll be looking for. I sometimes will rename that to VitOS just so that it looks fancy in my signal path captures, but there's no need to do that. Now I'm just going through and setting what my preferred defaults are for this DAC. I'd like the levels to be fixed. For this particular DAC, Roon detects it as 768 capable, but in my experience that doesn't really pan out, so I'd make some adjustments here. Make sure that the core encoder is on and the MQA support is turned off. And then, you know, everybody's got their own kind of routines. I like to go in here and change the icon to something that's pretty. I think I just picked a display because since we're doing this on YouTube, it looks sort of like a YouTube type of thing. I always like to turn volume leveling on. It makes the experience a lot nicer. You know, from my other talks that I'm a big fan of that. Wish it was the default for Roon, maybe someday. And then we'll just cue up some music and check the signal path and see if we have any output. And boom, there we go. And if I actually had sound coming out of the thing, you'd be able to hear beautiful music from John Williams. That's me just holding my phone and, you know, enjoying the experience. So that's pretty much the whole assembly process from start to finish. Again, it's pretty straightforward if you just follow the instructions on the VitOS webpage to run through that stuff yourself. The parts, I'll include a parts list in the description, but Raspberry Pi, I bought the 4 gig version. I really only needed the 2 gig version, but it wasn't in stock and I wanted something for this recording, so I wanted a fresh Raspberry Pi, so I bought the 4 gig version, but it'll work with either the 2 or the 4 gig. I know that the previous version of VitOS didn't work very well with the 8 gigabyte version. I haven't tested with this one, but I'd be surprised if it didn't work. The Flirt case, also, you know, about the Raspberry Pi is normally $35. The 4 gig one is $55, but you don't really need that for this. The Flirt case is another $15.95. The power supply is $8. And then the little SanDisk memory card is, I think it was $13 or something like that. So I don't know what we're up to, but maybe around 50 or 60 bucks. You can put together a very high performance endpoint that performs, at least in my estimation, about as well as any commercial endpoint that you could want to use. I haven't done a direct comparison between this and my Allo US Bridge signature, but you know, in my informal listening, I would say the performance is really, really close between those two. It's just I think it's a nice solution. It's pretty simple to set up. I know the Ropey guys are like, well, you know, you can. Ropey doesn't really require any configuration at all, and you can just set it up. But the thing that frustrated me about Ropey, when I went into the web interface, if I want to change the time zone, because I'm not in the UK, and it doesn't matter, I don't need to change the time zone, but I felt compelled to do it because there was an option there. Any little change that you make requires Ropey to reboot itself, and that was kind of annoying to me. For this solution, you just connect to the mobile app. The only option is just to install Roon Bridge or to restart Roon Bridge. There's no need to restart the device itself, and it's pretty simple. So if you're in a situation where you have a network connection, a wired network connection to where your audio equipment is, and you have a USB DAC there, and you want to get it networked in a very high quality way and without spending too much money because you're not sure if you're going to keep this thing forever, or you just don't want to spend money that you don't have to. Wired network connection, USB DAC, then this solution I think is one of the best solutions out there. I would also point out that, like I said, the folks over at Silent Angel have a number of other products. They've got a network switch that's audiophile quality. I don't know much about audiophile networking. I'm skeptical, but at the same time, there are a lot of products that address a need, so that suggests that maybe there is a need. It's something that I might explore down the road. They've got a fancier endpoint that also runs VitOS, but it's on a more robust hardware platform and a nicer chassis that might be worth exploring for folks with deeper pockets. Anyway, there's always new things, right? So in a few months, there'll probably be something else that's an interesting endpoint solution. But it's fun to experiment, keep an open mind, and explore these things. I'm going to look and see if we have any questions real quick. I don't see any. So with all of that, I think I'm going to draw this thing to a close. I appreciate your time and attention. It's been fun walking through this stuff, and hope that you found the presentation useful, and that you'll be able to apply some of this stuff to your own kind of network experiment or Roon experiments at home. Again, Merry Christmas, Happy New Year. Great to see you all, and look forward to seeing you again in 2021. Cheers.